All right. Today we're going to start the second lecture of uh, chapter number 4. And our learning goals for today are: the first one, relate mass and weight. The second, comprehend the effect of action-reaction pairs, Newton's third law of motion, and then how to draw a free body diagram. So the first thing that we're going to deal with here is basically the difference between mass and weight. And we state at the top here, mass characterize the inertial properties of a body. So we call that inertia. And I went to Google and I looked at Oxford Languages just to give you the meaning of this word. We call it inertia. And the dictionary gives you two meanings. The first meaning, a tendency to do nothing or to remain and change. And it says the bureaucratic inertia of various tiers of government. That means no one is doing anything about it. And then there is another definition from physics, a property of matter by which it continues in its existing state of rest or uniform motion in straight line unless the state is changed by an external force. So you know that inertia is basically resisting any change. So, and that's why we say that here, the mass characterized by the inertial properties of a body. Now, you all learned in the previous lecture about Newton's second law, and we said that the force or the net force is equal to ma. So in accordance with this, the greater the mass, the greater the force. So the mass plays a role. So now, if I look at the figure that we have here, we have an empty bucket, and then we have here a bucket full of sand. And we say that both of these objects at rest. That means V is equal to 0. In accordance of inertia, they'd like to stay at rest. They resist any attempt to change its state. And by the way, if you want to make any change, you will find that you will have to exert more force to move this because it has more mass. And this is where you're going to see the effect of mass. Now, you look at the figure that we have here. Someone is moving in straight line with uniform motion. That means constant speed. Now, when they apply the brakes, that means they're going to go through a change. But look at the driver. The driver is leaning forward and the seat belt is doing its job now. Why is that? Moving object at constant speed like to keep moving. So they're going to resist any attempt to change the state of motion. And that's why they react. And this is the meaning here of what the meaning of inertia. Okay. Meaning this is in accordance of Newton's first law, and the first law is called the law of inertia. And if you go, if we go to the slide here, where I gave you the definition of the meaning of inertia in physics, a property of matter by which it continues in its existing state of rest or uniform motion. That's in Newton's first law. In a straight line, unless the state is changed by an external force. And that's why here we said this is Newton's first law is called the law of inertia. So inertia basically try to resist any attempt for a change. And it's a property of what? A property of mass, or as the definition that I showed you, it is property of matter. So that's what a mass is. Now, weight is different. Weight now is a force, okay, exerted on a body by the pull of the earth. That's if you are here on the earth, the weight will be exerted by the pull of the earth on the object. If you are on a different planet or on the moon, for example, you will experience a different gravity, okay, and the weight will be different. So, for example, you have a dirham here of mass m, and you release. It will fall down because of what? Because of gravity. And the gravity is pointing toward the center of the earth, which usually, in your case, it's the vertical to the surface where you are. Now, we learned that in Newton's second law tells you that the summation of the force is equal to ma. Or we say that the net force is equal to ma. In a situation like this, the only force that you see acting on this dirham is the weight. So the total force is going to equal the force of the pull of the earth, and we give it a symbol W here, and we call it weight. And since this should equal to ma, and your A here is equal to G as a vector, so it will equal to mg, and that's what the weight is. But when we talk about in terms of magnitude, so we say that the weight is equal to mg. So usually it's given as a magnitude, and it's given as mg, where m is the mass and g is the acceleration due to gravity. And of course, as we stated earlier in chapter 2 and 3, the magnitude of a g is 9.8 meters per second squared. So here we define the magnitude of the weight as mg. And this always acts toward the center of the earth, which usually being the vertical or the normal to the surface where you are or where the object is. That's basically acting toward the center of the earth. Is this clear? So that's what the weight is. But you know that this value of g will depend on altitude. And probably I will deal with that in chapter number 5 when we talk about universal law of gravity by Newton. It depends on the distance between the centers of the two objects. So there will be differences if you go higher and higher. And of course, if you go to different planets, or you go to the different or the moon, for example, you will have a different g. So we always say that the g is about 9.8 meters per second squared. within practical heights that we have here above the surface of the earth, we can approximate it to be that much. But there will be variation if you go higher and higher. And that's why you experience weightlessness if you go higher and higher above the atmosphere of the earth. Okay. And notice the word weightlessness, because the effect of G is going to be less and less because you're feeling forces on you. But your mass is going to stay the same. So we say here, if we take an object and we measure its mass, and it is 1 kg, on Earth, we know that the G has a value, or the magnitude of G is 9.8 meters per second squared. So the weight here on Earth, which is equal to mg, will equal to 9.8 newtons. So the units of weights are the units of force, which is newtons. Now, if I go to the moon and I repeat the same experiment, the mass will be the same. It will be 1 kg, but the gravity on the surface of the moon, it's about 1.62 meters per second squared. So the weight there will be 1.62 newtons. So you can see that the mass on the Earth and on the moon, it's 1 kg, but the weight, which is a force, is basically less on the moon because the gravity on the moon is less. So we say here, the mass is the same on the moon on the Earth. Now, I want you to be careful here. When we say mass Earth, we mean mass on the Earth. And we say mass moon, we say mass on the moon. They are equal. We do not, and this I just want to make sure, we're not saying that the mass of the Earth is equal to the mass of the moon. What we're saying is the mass on the Earth is equal to the mass on the moon. And this is basically the difference will come to what will come in G. And that's the difference between mass and weight. And if you recall, in the beginning, we said mass characterizes the inertial property of a body. So here, you should notice the difference between mass and weight. Is this clear? Now, let's deal with this example here, where you're given a 2.49 times 10 to the 4 in Newton plane. You see Newton here, units. That means they're giving you the weight of the plane. They're not giving you the mass of the plane. Traveling in the positive x direction makes an emergency stop. The x component of the net force acting on it is minus 1.13 times 10 to the 4 in Newton. What is the magnitude of its acceleration? So now, you know, in the previous lecture, I told you that you always try to look at the forces acting on the object. So I told you always choose your x-axis along the motion, and the y-axis will be basically perpendicular to it. And you have to look at the forces that are acting on the plane. The plane is basically trying to stop, so they have to apply a force in the negative direction to bring the plane into a stop. So the weight of the plane here is 2.49 times 10 to the 4 newtons. The net force along the x-axis, it's equal to 1.13 times 10 to the 4 in newtons. And they ask you for AX. They ask for the magnitude here. But we're going to look at AX first. Now, whenever you have this, you have the net force along the x will equal to MAX. And you also have the summation of the force along the y should equal to MAY. But in this situation that we have here, there is no motion along the y. It's only moving along the positive x-axis, and that's why it's 0 here. So we're concentrating on the net force along the x-axis. And the only force that we have along the x-axis, it is the given net force, which is equal to minus 1.13 times 10 to the 4 newtons here. This should equal to max. Our mass, since we're given the weight, and we know that weight is equal to mg, so the mass will equal the weight divided by g, ax. So ax here will equal to the net force divided by the weight multiplied by g. I want to get the ax here, so I'll have to multiply here by g over w. It will cancel this from this side and gives the ax. So it is the net force multiplied by g divided by the weight. So the ax here will be minus 1.3 times 10 to the 4 divided by 2.49 times 10 to the 4 times 9.8. And that gives me minus 4.5 meters per second squared. Now, note that this is your ax, meaning the x component of the acceleration. And it's minus here. And you know, you want to stop. So you want to go from some velocity along the x to final velocity equal to 0. And that's why your acceleration has to be opposite to the direction of your velocity along the x-axis. But they ask about the magnitude here. And the magnitude, you always have to take what? You always have to take the absolute value. And that's why you have here 4.5 meters per second squared. And this brings in a point when you're doing your quizzes, you have to be careful. Are they asking you about the acceleration? If we ask about the acceleration, you have to include the minus sign. If we're asking about the magnitude, then you don't put the minus sign. You're just putting in the positive value or the magnitude. When you take usually absolute value, take this is in one component here, so you don't take the square root. It will be the square root of ax squared, but if it's in 2 dimensions, then it's the square root of the ax squared plus the ay squared, and so on. But I told you the ay here is equal to 0 because there is no motion along the y. The idea here, we needed the mass, but we're given the weight, and we got the weight we got the mass by dividing the weight by g. Is this clear? Is this clear? So that's the differentiation between mass and weight. Mass is going to stay the same wherever you are, but weight is going to be different depending on the gravity. And if you go higher and higher latitudes, that g may change for you and the weight will change. Or if you go to the moon, definitely you're going to have different weight. And that's why if you look at astronauts on the moon, when you see them walking, you see them hopping, because the effect of the gravity is less, okay, on them. Newton's third law, we did Newton's first law, and we did the Newton's second law in terms of mathematical format. The first law says that the summation of the force is equal to 0, or we can say that if net is equal to 0, and we said this is the law of inertia, Newton's first law. The second, it states that the summation of the force is equal to ma. The force basically depends on the mass and the acceleration. And I told you the force is a vector. And you see here the mass is basically scalar. And the acceleration is a vector. Newton's third law says if a body A exerts a force on body B, and we call that action, then body B exerts a force on body A, and we call that a reaction. These two forces have the same magnitude but opposite in direction. These forces act on different bodies. I'll try to explain what this means. So for example, we have here a ball B, and we have a foot that's kicking the ball. Let's give it a symbol A. Now, a force of A on B, you see the subscript here, that means the force of A on B, which is basically the force that's coming from the foot to kick the ball. Now, the foot, that's what we call the action here. There is an action on the ball, and that action is coming from the foot now. The ball has to react, and the reaction of the ball will be the force of the ball on A, and this is what we call the reaction. These two forces are equal in magnitude but opposite in direction. So if you look here, we have F of A on B equal minus FB on A. And we can also say F A on B equals F equals FB on A. That's also correct because we're only looking at magnitudes. But you cannot put an arrow on the top here. That will be wrong. So it's either these two are equal in magnitude or the two forces equal in magnitude but opposite in direction, and that's why we're including the minus sign here. Now, so these two forces act on different bodies, and this is what I don't want you to fall into. Someone might tell you that the ball here has a force applied on it, and the ball applies a force on the foot, but it's an equal magnitude and opposite direction. So if I take the net force of these two, that means the net force is equal to 0. And the question is why the ball is moving. That's wrong reasoning. Okay. You look at the force that is applied on the ball, and that should equal to ma. And from that one, you can basically figure out the acceleration and so on. But the force that is applied by the ball, it is applied on the foot. So when you try to analyze bodies, you look at the forces that are applied on them. And in this case, you look at the force applied on the ball to figure out the force that you can basically find in acceleration and so on. But you can look at the foot separately. But to look at the ball by the force that it is on the ball and the force applied by the ball, that will give you a wrong reasoning in saying that the ball should not move. Is this clear? Now, let's take another example here. And this example here, after your sports car breakdown, you start to push it to the nearest repair shop while the car is starting to move. They ask these questions. How does the force you exert on the car compare to the car exerts on you? You know right away by Newton's third law, these two forces are equal in magnitude and opposite in direction. So here, the driver pushes on the car, and the car will push back on the driver. So the car will feel the force that it's applied on it by the driver, and the driver will feel the force applied by the car on him. So for example, if there is no car in front of the driver, he will not feel. He will be walking, but he's not going to feel the effect of that car. But if he starts pushing the car, he's going to get more tired and feeling the effect of that. So there is a force exerted on him by the car. And by Newton's third law, it will be equal in magnitude and opposite in direction. In B here, how do these forces compare when you are pushing the car along with constant speed? Now, you know right away, when the speed is constant and you're moving in straight line, you know that your acceleration is equal to zero. So you always, if you want to use that reasoning and you say that if I look at the Newton's second law and I say that F is equal to ma, and I'm moving with constant speed meaning my acceleration is not equal to zero, that means probably the net force here will equal to zero. And you will say, well, the net force should equal to zero, so why should the car be moving? Or why should I have a force on the driver? It's still the same situation that you're dealing with. There is a force exerted on the car, and there is a force, the car exerts a force on the driver. And this is what we call the reaction. So we have both here. We have action and reaction. Okay? And they are basically the same as the situation that we have in A here. Is this clear? So let's take this conceptual example here. An apple sits at rest on a table in equilibrium. A, what forces act on the apple? B, what is the reaction force to each of the forces acting on the apple? What are the action-reaction pairs? Now, if you do your free body diagram, and I told you always take things from the center of the mass, you have a normal force, which is coming from the table that supports the apple. And the earth pulls on the apple with the weight. These are the two forces. So in A, they ask us about the forces that act on the apple. The forces that we see on the apple, we see basically the action in this case, it's an action force because it is on the apple from the table or the surface of the table. And we also see an action coming from the weight. And this is the force of the earth on the apple. Now in B, we look at the reaction. And if we look at the reaction, we'll have an N prime, which is the force of the apple on the table. And we see W prime, which is the force of the apple on the earth. The earth is pulling the apple downward, and the apple is pulling the earth upward. And you may see this is not possible. The apple is small, the earth is bigger. Okay, but that's the way you look at it in Newton's third law. So the action-reaction pair here is N and N prime. N is basically the action, which is coming from the table, and N prime is the effect of the apple on the table. And W here is an action, and W prime here is the reaction, which is the effect of the apple on the earth. So that's how you look at it. Now, there is always a wrong a view that some student might have, and they think of N and W as action-reaction forces. And this is the normal force is different than the weight. So for example, if you have an incline like this and you put a mass on top of it, the normal force is always normal to the surface, and the weight is always down toward the center of the earth, or along the normal to the surface of the earth. So you can see N and W here, they're not opposite each other, meaning they are not equal to one another. So I don't want you to fall into that trap thinking that the normal force and the weight are action-reaction forces, because this is the case. But to enforce this idea here of action-reaction, if you make a full fist and you hit the wall, you actually, if you hit it very strong, you may feel the effect on your hand. But I will say that you are the one who hit the wall. Why are you screaming? But by Newton's third law, the wall basically is hitting back, and that's the reaction of the wall. Is it clear now? Is this clear when we talk about Newton's third law, action, reaction, and so on?
Doctor, are we going to study how to measure the normal force?
Yes, we'll do that. Okay.
Okay.
So now, later on, I will in chapter number 5, we'll deal of how to calculate the normal force and so on. Now, here is another example just to show you these effects of action, reaction, and so on. You have a stonemason drags a marble block across a floor by pulling on a rope attached to the block. What are the action-reaction pairs? So you can look at the tension in the rope. Remember, ropes always pull. You know that ropes are flexible, so they cannot push, they always pull. So if you look at the block here, the rope is pulling on the block. And in this case, we can say that the block is pulling on the rope with T prime. We can look at the friction, because the block is resting on a surface, and there will be friction between the surface and the block. And if a friction is always opposing your motion, if the block is moving this way, then friction is basically operating this way. It should be from the center of the mass, but we brought it down here just to separate these. And F prime will be the reaction, which is basically the effect of the floor on or the effect of the block on the floor. Similarly with N, we'll have the normal force from the surface, and then the N prime, which is the effect of the block on the surface, and the same thing that we have for the weight, which is the force of the earth on the block, and then an N prime, W prime, which is the force of the block on the earth. And this is basically what we call action reaction pairs in accordance with Newton's third law. So two things that I told you have to not pay attention to is if the body has a force on it and then it reacts with a force equal in magnitude and opposite in direction, then the net force should be zero. I told you this is a wrong way of looking at that. We only look at the forces that are applied on the body. And the second thing that I don't want you to fall into, that normal force and weight are action-reaction forces. You may have different situations where the normal force and the weight are not equal. Now, this brings in to how you treat free body diagrams, and we can abbreviate that as FBD. And a free body diagram is a sketch showing all the forces acting on an object. You have to differentiate between a system and an object. Okay. So you always look at an object and you look at the forces that are acting on that object. So first point, draw a very simple sketch for the physical situation showing angles and dimensions, representing the body as a large dot, usually from the center of the mass. Ask yourself, what is interacting with the body? Draw a force vector to each interaction. Label each force with a symbol for the magnitude of the force. Draw angles accurately and label it if it makes an angle. So for example, you have two players here, basketball players. One is up in the air, one is basically on the floor. And we're asked here to look at the forces acting on an object. So if you look here, you will have the hoop, you have the basketball, and you have the player. So if I concentrate on the first player here, well, he's up in the air, so the only force acting on it is the weight, which is the effect coming from the earth. I'm not going to put W prime here, which is the reaction. I'm not going to include that. I only look at the forces that are acting on the object. The other player, which is standing on the floor, well, the weight is down, but also the normal force, which is the effect that's coming from the floor on the player. And these are basically the forces that are acting on the player. So in this case, there is only interaction between the player and the earth, and gravity. In this case here, you have interaction between the floor and the player and the interaction of the gravity with the player. Is this clear? So that's basically how we deal with that. Let's take an example here that may help us and do some of these problems. Boxes A and B are in contact on horizontal frictionless surface as shown. Box A has mass 17 kg, box B has 8.0 kg. A horizontal force of 100 newtons is exerted on box A. Draw the free body diagram for box A and box B. So you're looking at each object separately. What is the magnitude of the force that box A exerts on box B? So what we're going to do now, we're going to do a free body diagram, but we'll do it for each body separately. So if we look at box A, and when we look at box A, we have the normal force, and here we put a subscript A to denote that we're looking at the normal force on A coming from the supporting floor. And WA here, which is the weight due to A. And then we have the applied force. And then we have, because we're looking at A here, and B is here, so B is going to apply a force on A. A is going to apply a force, but B is going to apply a force by Newton's third law. So here, that's why we say there is a force of B on A. This force is applied by B in accordance with Newton's third law, but it's on A, so we include it here. Now, if I want to look at box B, on box B, I have the normal force, and here it's in B, denoting that it's on B. And I have the weight, which is WB. And then I have the force that's coming from box A on B. which is this way here. Of course, B here will put the force B on A equal magnitude opposite direction, but it is on A. So here I don't include that. I only include the forces that are on B. Now this is a system, and this system will move with the same velocity, will move with the same acceleration. So that's why we say that velocity of A equal velocity of B is equal to the velocity of the system. The acceleration of A should equal the velocity, the acceleration of B. It's the acceleration of the system. Now, the force applied on A, the force applied by A and B should equal in magnitude the force applied by B and A, and it should just equal to, we give it a symbol P here. Now, I am going to look at my equation of motions. So I look at the summation of the force x on A, which should equal to MAAX. Now, you can also say that you have Fy, which is equal to MAAY. Okay. But you have no motion along the y, so that's basically equal to 0. So the only motion is happening along the x. So when you look at A, you have the applied force along the positive x-axis. You have the Fb on A, which we said it's equal to P. It's in the negative, so that's why we have F applied minus P equals MAA. Along the B, I don't need it in chapter number 5 when we want to deal with the friction. We have to calculate the normal force in order to look at friction and so on. But here we have no frictions. For B, again, along the Y, it's 0. Along the X, I only have the force of A on B. So, which should be equal to MBAX. And so P here will equal to MBA, and A is the same in both cases. So now this is my first equation, that's my second equation. I can basically add the two equations. I'm adding 1 plus B, and if you do that, P here is negative, P here is positive, they'll cancel out. So what you will have the applied force equal to MAA plus MBA. A here is the same for both of masses, and you can take here A as a common factor. So you'll have here MA plus MB. So your acceleration here will equal to the applied force divided by MA plus MB, which is 100 divided by 17 plus 8. 17 plus 8 is 25. 100 divided 25 will give you 4 meters per second squared. And you obtain the your acceleration. They ask you here the magnitude of your force. So from 2 B here, which will be equal to the mass of P multiplied by the acceleration. Mass is 8, and the acceleration is 4, so you get 32 newtons, and that's the force basically exerted by A on B. And that's how you handle systems and so on. Is this clear? Is this clear?
Doctor, I don't understand what P is.
P is just a symbol, okay? You have two forces here. You have a force which is F A on B, and you have a force here which is F B on A. You know these two forces, right? They should be equal. Okay, we just said that these are equal to P. instead of using a symbol F, because we have F applied, we change that to P. We just use a symbol for that. So
And
you
we're
can look
only
at,
taking their magnitude, right?
of course, in this case, yes. There,
Okay.
that's why if I put an arrow on the top, I say this is basically the force. But I did not put an arrow on the top. I'm just saying that they're equal in magnitude and they should equal to P. Is it clear now?
Yes, thank you.
Another example here. Two connected crates with mass 4 kg and 6 kg sit on a frictionless surface. A woman pulls horizontally and the 6 kg crate with a force F that gives the crate an acceleration of 2.9 meters per second squared. Find the tension T in the rope, calculate the force. Again, it's one system because the rope is stretched, so they will be moving with the same velocity, they will be moving with the same acceleration. So if I look at the first one here, then I will have the weight WA, I have the normal force in A, and then I have the tension. The tension here will be pulling that way on mass A. But on mass B, the tension will be pulling that way. So always when you have cables or when you have ropes, okay, and you want to look at a different object, you want to look at the effect of this rope. So in this case, the rope is pulling this way, but in this case, the rope is pulling the other way. And some people say, how come the rope is stretched and the effect of these should be as I drawn it here. Is this clear? So now, these are the forces that you have an A. On B, you will have WB, you will have NB, you have the applied force, and then you have the tension which is acting this way on B. Now, if I look at the equation of motion, the net force on A should equal to AX, but since it's a system, okay, it will be the same acceleration. And we said A here because you can look at the Y component and you can say it's equal to MAY, but there is no motion along the Y, it's equal to 0. Maybe later in chapter number 5, as I told you, when we look at friction, we have to include the Y component in order to calculate the normal force, which we will use in calculating friction. Now, the only force that you have along the x-axis is what is the tension. So tension here will equal to MAA. You're given the acceleration, which is 2.9. Mass A is 4, and that will give you 11.6 newtons. For B, if you look at your equation of motions, if you look at the force X along the B or on B, it will equal to MBA. And if you look at them, you have F going along the positive x-axis. The tension is going along the negative, so it's F minus T should equal to MBA. What you're interested in figuring out the applied force, so you can take this to the other side with a positive sign, and that's why you say the F here is equal to T plus MBA, which is T already found, it's 11.64 plus 6 times 2.9, and that gives you 29 newtons. Is this clear? So that's basically how you draw your free body diagram, how you basically start analyzing the motion. We'll try to look at some 3 questions here, basically, to test your understanding. In question 1 here, you are standing at rest and begin to walk forward. What force pushes you forward? So you look at your foot here, and we say the force on the floor from your foot, you push backwards with your foot. but the friction force on the floor, on the foot from the floor, this is what basically the reaction force in this case, and it pushes you forward. So when you try to move, okay, is the force that you apply on the floor is going to cause this, or the force of the floor that's applied on you will cause you to move? Which one? And which of these options should be the right option here? So when you think about it, it will be the force of the ground on your feet that will basically cause you to move. We did not talk about friction. Friction in this case is important, otherwise you cannot walk. Okay. Question 2 here. They ask you to draw a free body diagram. And remember, we said always when you draw a free body diagram, you look at the interaction of the forces on the object. You have the car here. The car is an incline. Normal force is always normal to the surface, and we take it always from the center of the mass. The effect is always around the center of mass. Weight going through the toward the center of the earth, which is along the normal to the surface at your location or at the car location. And the tension, which is basically pulling the car this way, and it makes an angle of 31 degrees. So you really have to look at these forces, and you also make the angles. Later on, if we want to analyze these problems, I may say that you choose the x-axis to be this way and the y-axis to be that way. That means you eliminate the motion along the y and you only have motion along the x. But we'll do that in chapter number 5. Is this clear? In question 3, in question 3 here, we're dealing with, again, free body diagrams. If you look at the situation that we have here, we have the weight is pulling down. The person here is exactly in the middle, and the angle is the same. So there is a tension here and tension there. And that's why what we have here, T, and we have the weight pulling down toward the center of the earth. In this situation here, you have mass A and the weight, and then you have a point here, a knot that connects the 3 ropes. So this rope and this rope and this rope, they are not the same rope. They're tied up point here. So if I want to look at the free body diagram for A, I will have the normal force. And I put N here because I don't see anything on the weight. So I'll just, but here I will put WA. And of course, T3 will be pulling the mass this way. Now, if I want to look at the weight, I have the weight is pulling down, and then the tension is pulling up. I will say that this is T1 because this is rope 1 for me. Now, again, you should not put a normal force here. Normal force only comes when there is a supporting surface. And here there is no supporting surface. I don't want you to fall into this. And I already told you that you should not think of the normal force and the weight as action-reaction forces. And that's why whenever you see a weight, you would put a normal force opposite to it. Don't do that unless there is a supporting surface. So that's, in this situation here, we don't have a normal force. Now, these 2 ropes, 3 and 1, they are basically tied up to this point, and they tied up by another rope here. And that's why we have here the rope is pulling that way, T2, T3, and T1. So we get a relation between these 3 tensions, and T3 is applied on A, and T1 is applied on W, and that's how you identify the different forces on the different object. You have a system here, but you look at each object separately within this system. And as I told you in previous lecture, you always choose X and Y. You can always choose X and Y for each object separately, and we'll do that chapter number 5. So what we basically covered today is distinguish between mass and weight, Newton's third law, action-reaction, and free body diagrams. So if you look at the Newton's 3 laws, the first one, which is summation of F is equal to 0, or we can say that the net force is equal to 0. Second law, summation of the force is equal to MA, or the net force should equal to MA. And the third law, FAB equals minus FBA. Or you can say FAB should equal to FBA. Note I don't have an arrow on the top, I'm just only looking at magnitudes. But you cannot say FAB equals FBA. That's wrong, because you have a vector sign on the top, and of course these two vectors are equal in magnitude, which is here, but opposite in sign. Is this clear? Is this clear? Any question on this? Good.